Hello, everyone, and welcome back. In this lecture, like many of the previous lectures, we are going to focus on one big theorem, and we're going to work up to stating and proving that theorem. Now, today, that theorem is going to be the Heine-Borel theorem. So this is another one of those essential results in modern analysis. And the Heine-Borel theorem is named after Edward Heine and Emil Borel. But it has a very, very interesting history that I would highly, highly recommend you maybe looking into on your own. Because when modern analysis was being formulated and its foundations being put in the 19th century, it turns out that a lot of the most famous mathematicians that were working at the time had versions and proofs of this theorem. So from my understanding and my research, the first actual proof of this goes all the way back to Dirichlet. But we had people like, of course, Heine and Weierstrass, and then Borel, Lebesgue, all kinds of these huge names in mathematical analysis that have given us proofs of this. So it's very interesting that Heine and Borel got their name on this, even though tons of these mathematicians contributed to its modern statement and its relatively simple proof that we'll see today. Now, of course, one aspect of this is that Dirichlet and Lebesgue and some of these other big names, Weierstrass, already have enough named after them. But that is also true for Borel. Borel has quite a bit named after him as well. So it is interesting how we decided to name this after two of these mathematicians and not all of the other ones that contributed to the theory. Now, nonetheless, this lecture is going to be slightly different than some of the previous lectures. We're not going to focus as much on sequences. We're going to focus more on intervals. So it's going to be similar to what we talked about with the nested interval theorem, where we focused much more on intervals than we did on sequences. Now, to start this lecture, we're going to have to start by introducing some more definitions. That's how all of these lectures get off the ground. And today, we're going to start with the definition of what's called an open set. So the first definition of the day, we're going to say a set. Now we're going to say O, and this stands for open. Well, this thing is called open. Let's put it in red so that it's emphasized here. It's called it's called an open subset. We should be very careful. So it's sort of abbreviated to just be called open, but it's an open subset of the real numbers, provided that for each element of this open set, there exists an R sub x. So this R depends on x. That's why I have the subscript x here, such that x minus rx, so the interval x minus rx and x plus rx is entirely contained in the open set. Now, what does this say? This says every point in the set has a little bit of wiggle room, right? You can go a little bit to the right and you can go a little bit to the left. All that matters is that r, which is what we refer to it as a radius, all that matters is that that thing is positive. It could be extremely, extremely, extremely small, but it has to exist. I have to be able to go a little to the right and a little to the left. And the sort of canonical example of this, you are probably already familiar with, and that is open intervals. So maybe you've never thought to yourself, why is it that we refer to these things as open intervals? Well, this nomenclature, this terminology comes from this more general definition of an open set. So we claim that every open interval, so let's say A to B, is an open set. So the way that we need to do this is we need to pick any arbitrary element in here and show that there exists a radius so that we can sort of wiggle to the left and the right in here. So take x in this interval, which means that A is less than X, which is less than B, right? So it's just important to remind ourselves what this actually means. And let's define the radius to be the minimum of the distance from x to a and the distance from x to b. Remember those absolute values? That's a distance measure on the real line. Clearly, this thing is positive because x is between a and b inclusively. Well, then we have that this interval, so if we go rx units to the left of x and rx units to the right of x, we are still in our open set. Sorry, this is the interval a to b. And this just comes from the fact that we are restricting ourselves by this definition of the r sub x, this radius, as saying you can't move farther than the distance from x to b on the right and the distance from x to a on the left. And that means that your interval is entirely contained inside of this big open interval. Now, open intervals, it turns out, are sort of like the fundamental building blocks of open sets. And that becomes apparent through the following theorem here. So the theorem says that every open set, so every open set O in R doesn't have to be an interval, but this is a union, right? So this is, you think of union as sort of addition of sets, right? Putting sets together of, now this is perhaps infinitely many open intervals. And moreover, every union of open sets is an open set. So this is kind of interesting, right? This sort of tells you that open intervals are the fundamental building blocks of open sets, because it says any open set that you ever can find in the wild, well, that thing has to be sort of thought of as being built up from open intervals, right? That's why we're thinking of this union. Similarly, it says that if you take a union of open sets, so say take two open sets, you put them together, you build a new open set when you take a union of these things. So this actually is very, very interesting. And if you ever find yourself in a topology class, this becomes extremely important for how you understand a topology. This is actually a definition of a topology on the real numbers. Now, we're not going to go into the topology realm here. We're going to stay in the analysis realm, but I did want to make the connection just in case this piques any interest. Okay, the proof of this is surprisingly simple. So let's say let O be an open set. Okay, so I start with an open set. Then, by definition, so I'm using the definition of an open set, nothing more. For all x in O, there exists an r sub x greater than 0, such that x minus r sub x and x plus r sub x is contained in the open set. But this means that if you take the union over all x's in here, all of these little open sets, these things are all contained in O, right? So every single element of X has its own radius that gives you wiggle room inside of the set O. Every single one of those intervals is contained in the open set. And so then when you start putting the intervals together, all of them are contained in the open set under this union. But similarly, if X is in O, then X clearly belongs to this union, right? Because I'm going over every single X here. And so I have that the union is a subset of the open set, but also the open set. So the open set is a subset of the union here now. And if two sets are subsets of each other, A is a subset of B, B is a subset of A, this tells me that my open set is equal to this union. And the interesting thing here is that that union is itself a union of open intervals. So that's exactly the first piece of this. Now we prove the next piece. We say, let's take a union of open sets, and we're going to show it is again open. So now, to prove the second conclusion, let's let O equal to the union of a collection of open sets. So I'm going to say alpha belongs to A, and this is B any. So let me finish writing this before I start talking about it. Open. So this is a very common mathematical notation here that's being done. We say alpha is in A. So we say, pick any index set. This could be the entire natural numbers. So you say 01, 02, 03, 04, 05. Or it could just be, 4 different open sets, right? 01, 02, 03, 04. Or this thing could be massive, right? This could be all of the rational numbers. Maybe you're doing some weird indexing where you're indexing by the rationals. Or maybe this is all the real numbers. The point here is that A is a general index set, and we just say, you go over every element of A. I don't care if it's big or small, whatever it is. It's the same thing that I did here. In the last example, I have a union over all x's belonging to my open set. Now, that could be huge, right? That could, imagine your open set is the entire real numbers. Well, then essentially you're taking a union over all the real numbers. So I don't want you to get hung up on the notation here. This is just common sort of math speak to say, general collection of sets. Then we want to show that this O is open. So we want to say, let X be an element of the open set. So in the union, okay? And we want to show that there's wiggle room associated with this thing. So we know, since O is just a union, if you're going to pick an element here, there's got to be some element of the index set such that X belongs to the open set that builds this up. Remember, we think of unions as being ways to construct bigger objects. And so if you're saying something's in the big object, it had to come from one of the smaller objects. And this thing is, of course, open. But thus, since O alpha 0 is open, thus there exists some radius such that, now let's do a string of inequality or a string of subsets here. There's wiggle room inside of O alpha 0. But of course, O alpha 0 is belonging to this huge union because it's just one of the building blocks used to build it, which is equal to O. But that means that that X has a little wiggle room around it inside of the big set O. So thus, O is open. So there we go, right? We can kind of think of the union as helping us to construct bigger open sets. And importantly, the sort of fundamental building blocks, the atoms that make up these open sets, are the open intervals. Okay, so getting closer to the Heine-Borel theorem, we need another definition here. So it's similar to that of open sets, but this is called an open cover. So an open cover of a set S, which is a subset of the real numbers, is a collection. So it's a collection of open sets. So you call it O, and this is O sub alpha of alpha in A. So again, you see that notation of just some general collection of sets. And this is of perhaps infinitely many. So you keep that in mind. It could be finite, could be infinite, doesn't matter. Infinitely many open sets, O sub alpha, where alpha ranges over some index set A such that the whole thing, S, the whole set is contained in the union of all of these open sets. So that's the idea of an open cover, right? You have a collection of open sets. When you put them all together and build this huge mega open set given by the union, well, then that contains your entire set S, right? So that's what this is saying. We know from the previous theorem, this thing is open by previous theorem. So that's why we know that we call this thing an open cover, right? You've sort of covered the whole thing by an open set. The cover part comes from the fact that you have a subset here. So maybe we should just put a little note that this is where that sort of cover notation comes from. Okay, so let me give you an example so you can sort of cement this in your mind, so you can try and understand this, because I understand this is a little more abstract than maybe what we've been looking at already. Maybe we're getting very good with sequences. We've done a lot with sequences now, but now we've sort of switched gears in the past lecture and this one into more interval-based analysis. And so things are starting to get a little foggier again, right? We're sort of having to build up some intuition. So let's say consider the set. Now, S is going to be the open interval from 0 to 2. And this is a finite open interval. So we claim that S is contained in the union of n equal 1 to infinity. So in my case, my index set is all of the natural numbers. So my A from the previous definition would be the natural numbers. And it's contained in the union of this collection of open sets. So here is, each one of these is an open interval. And I'm claiming that the set of 1 over n to 2, those open intervals, form an open cover of my set S, right? Again, it's covering because it's contained in the union. Well, how do we prove this? So maybe I'll move to the next page so we have lots of room here. But the proof, we say for each, so we pick an element in S, which is just the interval from 0 to 2, which implies 0 is less than x, which is less than 2. Well, then from the Archimedean property, there exists a natural number n such that x must belong to the set 1 over n comma 2. So, i.e. x is bigger than 1 over n, right? So no matter how small x is, it's positive. And so therefore I can wedge a value of 1 over n into that thing. So let's look at this on the number line for a second. I've got, let's say 0 here, I've got 2 here. And then I will say this is my value of x right here. Well, I have, say, 1, which is just 1 over 1. And let's say I have 1/2 here. And then I've got maybe 1/3 here and a quarter here. And things are going down and down and down. And as long as I have separation from x to 0, you can see that I can always wedge a 1 over n in there, because the 1 over n's we know as a sequence are converging to 0. So thus, x is in here, which belongs to the full union, which implies that this set, so this big union, 1 over n to 2, is an open cover. Of S equal to 0 to 2. All right, so it's not really that that interesting, but it's important to sort of formulate this and see how it works, right? The proof was pretty quick and easy, but again, most of it comes from really understanding the definition here. Okay, so let me show you now. Let's go to the big result here, and let me show you the Heine-Borel theorem. Now, the Heine-Borel theorem talks about open covers, but it figures out a way for us to use open covers fairly sparingly. So maybe your collection of open sets is enormous, but what the Heine-Borel theorem is going to tell you is that if you're trying to cover a closed interval, then you find out that you actually don't need an enormous collection. In fact, you only need finitely many open sets to cover a closed interval. So let me state it for you, and then we'll talk about it, and then we will prove it. So actually, sorry, I should point out, this is the Heine-Borel theorem. Again, it's named after people. It has a name. That means that we can easily refer to it as mathematicians, and everybody sort of knows what it is. And that means it comes up a lot, right? We only give theorems names if they come up a lot, because we have to be able to refer to them and have everybody know what we're talking about. Okay, so suppose the closed, now this is a finite interval. Of course, I am only going to talk about finite intervals, and that means that A and B, the endpoints, are themselves real numbers. Nothing is infinity here. This thing is contained in the union of a bunch of open sets. So I've covered it, or I've covered the closed interval AB. So where this big thing is equal to this collection of open sets is an open cover of the closed interval AB. Then there exists a finite set. Let's call it F for finite, and this is going to be a finite collection of the indices. So a finite sample of the set A, such that, in fact, the interval, the closed interval, is covered by this, just the elements in A. So alpha in F, sorry, of O alpha, which is just this finite union of open sets. Sorry, this should be, let's say, K equal to 1 to N of O alpha K. Okay, so before we go into the proof, let's talk about this for a second, right? So what does this say? You know, on the surface, it doesn't look like it's that powerful of a theorem, but you know, as we're going to see as we progress through this class, we're going to use it a little bit more, and you're going to see this is in fact a very powerful theorem. In fact, again, if we evoke topology for a moment, this becomes an extremely important theorem in topology because this helps us classify what's called compactness. Now, in the realm of analysis, we're not going to get into compactness too much, but essentially compactness means closed and bounded. Now, a closed interval is closed. It sort of means not open. Now, we can make that more precise if necessary, but for now, we can leave that as imprecise. And bounded means the interval has finite length. So what this says is that if you have some massive collection of open sets, well, you're overdoing it. You don't need to use all of those open sets. In fact, only finitely many will do the trick. Now, I want to go back to the previous example, right? We used the open interval 0 to 2. It's not a closed interval. It's pretty easy to check that you can't cover this open interval with a finite collection of these 1 over n to 2s. If you try and do that, you're going to be missing a little gap near 0 because you need infinitely many of the 1 over n's to get yourself all the way to the left to 0. Now, what's the issue? The issue is that the original set S was open itself. It was an open interval. So the Heine-Borel theorem doesn't apply. It only works for closed intervals. This is a massive caveat that you have to keep in mind when you are working with the Heine-Borel theorem. And the cool thing about the proof of this, we're going to see, is we're going to use the nested intervals theorem. It's a lot of interval halving, so it's going to be a lot of fun. So let me start on a nice new fresh page, and let's look at the proof of the Heine-Borel theorem. Okay, so we're going to assume the theorem is false. So we assume the theorem is false. So we're going to argue to a contradiction, right? So we're going to say that that if we assume that we have a cover of the closed interval that's infinite, we can't find an open subcover. And what we'll do is we'll sort of argue our way through this proof until we get to something that makes no sense. And we'll see that the only way for this to have worked is if we actually did have a finite subcover, right? Something was logically inconsistent there, and it was the assumption that we didn't have a finite subcover. So that is, assume the Heine-Borel theorem is false. So thus, we can assume the given cover has no finite subcover. Remember, the Heine-Borel theorem says that if you give me a cover, there is no finite, or sorry, there must be a finite subcover. So I'm going to assume this is false. I'm going to say, assume there is no finite subcover. Well, here's where the fun starts, right? So we're going to say, let's let A1 equal to A and B1 equal to B, and let C equal to the midpoint. So a classic method of proof that we've been going through in this class. So then each interval, let's say A1 to C and C to B1. So each of the halves is also covered by, the open cover, right? So this big union, alpha, right? So again, that's just because these things are subsets of the original interval, and the entire interval was covered by this union. So you have this sort of transitivity that applies across here. So if both of these intervals had finite subcovers, right? So we assume the big interval A to B has no finite subcover. So then we're saying, okay, these smaller half intervals are both covered by the original open cover. And if both of these had finite subcovers, then the whole interval, so A to B, sorry, would have a finite subcover. And this just comes from the fact that since the union of two finite families so it's a lot of writing for now, but it's important that we iron all this out, is still finite. So imagine, we said maybe the left half, it takes 10 open cover, or it takes 10 open sets to cover, and the right half takes 20, whatever it is, pick two finite numbers. Well, then that means that if I take the union of both of those, the 10 from the left and the 20 from the right, I have at most 30 open sets, again, finite, and it covers everything, right? Because the 10 cover the left half, 20 cover the right half, put them together, you've got everything covered. This would be a contradiction, right? We said that we don't have a finite cover of the full thing. So since we supposed AB has no finite subcover, then one of those half intervals has to have no finite subcover as well. So we can pick a half interval, and we're going to denote it exactly what you can guess, A2, B2, that has no finite subcover. Okay, so what did we do? We kind of did the same thing that we did with, say, like with all of our interval halving, right? We're sort of tracking, which of the half intervals maybe has the element that we're looking for, or which one has infinitely many elements in the Bolzano-Weierstrass theorem. We're doing the same kind of thing. We're saying you start with a whole interval that has this bad property of no finite subcover, then break it into two and ask which one of those has no finite subcover. And it might be both. In that case, just pick one of them. It doesn't matter. But then you just repeat the argument. So you have this sort of inductive logic. So now we can cut A2, B2 in half. And reason again. So reason the same way for A2, B2. So this new interval as we did for A1, B1. And that means that there's a half of this interval that can't be covered. So that tells us we obtain, so you can sort of repeat, you sort of automate this, you put it on loop. So we obtain a decreasing nest, there it is, right? This is evoking the previous lecture of intervals, which A1, B1, that was our original interval, then A2, B2, that was the half of that doesn't have a finite subcover, and then A3, B3, and all the way down, AK, BK, keep it going. You have infinitely many such that each AK, BK is covered by that big union, but has no finite subcover. Okay, so it kind of feels like we're really in the weeds, right? We're kind of way down the rabbit hole. So maybe it's worth pausing the video for a second and trying to figure out how we're going to get out of this, how we're going to come back up. Where obviously we have a nest of intervals. That means we're going to use the nested intervals theorem. But try and think of this, try and beat me to the conclusion here. So I'm going to keep going, but I want you to try and pause and think this out. Well, since we have been doing interval halving, we know that the distance from, or the length of each one of these intervals, the distance from BK to AK, this is the distance of the original interval, B minus A, and then halved K minus 1 times, which, from the same things we've been doing over and over and over again, this thing goes to 0. And so by the nested intervals theorem, there exists a unique, right? So the nested intervals theorem says if you have this nest where the width of the intervals is going to 0, there exists a unique x that belongs to the intersection of every single one of these intervals, so AK, BK, which is contained in the original interval AB. Now, since x is in AB, then there exists some alpha in A such that X belongs to one of these open sets. And that comes from the fact that the union of all these open sets covers the original closed interval AB. So if you pick a point in the interval, you have to have it contained in one of those open sets that are used to build the cover. But now that means it belongs to an open set. So from the definition of an open set, there exists a radius such that you can wiggle this thing around so that x minus rx and x plus rx is contained in O alpha. But then what we could do is we can go back up, right? So we can go back out from the limit. So now pick K big enough. Now I'll show you why I mean big enough. I'm being a little loosey-goosey here. So that BK minus AK, so the width of this interval is smaller than your radius Rx. Now you can always do this, right? This is the definition of conversions. So I just didn't say, there exists a capital K such that for all K, blah, 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 blah. I skipped it. I said, just there's K big enough that this is going to be the case because this thing is going to 0. So thus, this thing has a smaller radius. The distance from BK to AK, which also contains X, right? So let me write this down. X belongs to that interval, AK to BK, by definition, because it belongs to every single interval from the nested intervals theorem. But this thing, because of my choice of K, is contained in this open set because Rx is bigger than the distance from BK to AK, or vice versa, AK to BK. But again, by definition, this thing belongs to O alpha. But now let me underline this. Look what I did. All right, so maybe I can write this in blue underneath just to really highlight what happened. I covered one of the uncoverable sets. And we have covered, so let's scroll up this. We have covered AK BK by a single, like one, not even finitely many, like one open set. O alpha from the original cover. This is a very small finite cover. This is a extremely small finite subcover. Finite subcover of that interval AK BK, which contradicts the statement that this set AK BK could not or does not have a finite subcover. Right, so remember, we went way down the rabbit hole, but what happened was that every single step, every single closed interval that we created, we said it has no finite subcover. But now we found a problem, right? Well, actually, one of those sets had to have a finite subcover. So this contradicts, or this contradiction proves the Heine-Borel theorem, right? Because our assumption was if the Heine-Borel theorem is false, there is no finite subcover. And then we followed the logic here to define these nested intervals. And then we showed that, the logic it couldn't have worked. And that sort of destroys this house of cards and brings everything down on us and tells us that, in fact, the Heine-Borel theorem has to be true. Now, what I want you to really take note of is why we needed a closed interval for this, right? So, and the short answer is we needed closed intervals in order to provide or to use the nested intervals theorem. right? The nested intervals theorem will not work if you use open intervals necessarily. And so therefore, we need to have a closed interval for the Heine-Borel theorem to work, right? We need to have this limit point of x that belongs to all of these little half intervals. And we need to use that value of x to arrive at our contradiction. So this is very, very important. And we saw an important counterexample when we have an open interval. The example that we did right before the statement of the Heine-Borel theorem, when you have an open interval, you can't necessarily cover it with a finite subcover. It's a very, very important nuance to everything that we're talking about. And this is only going to work for closed intervals.